this one we're given the equilibrium constant mKa, and we are calculating our equilibrium concentrations. So let's start by kind of setting up our tools, our Rice table and our equilibrium constant expression in terms of X. So let's start reaction. The reaction for an acid will always just be it in the unionized form going to the ionized form with a hydrogen off the front taken off. For the initial, always use this. This will be your initial for the unionized part. And then 0 for these. For the change, this is where we are going to subtract off the amount that ionizes. So it gets added over here. Our coefficients on these are all 1, and they will be. So a few things to notice. So X is the amount that ionizes, but even more exciting than that is X is our hydrogen ion concentration at equilibrium, and we can use that to get to pH later, so that's something to kind of think about. Okay, and that all kind of got in the way of my Rice table, but at equilibrium, so what I was saying was this right here. Okay, so we have our equilibrium expressions in terms of X. Let's set up our equilibrium constant expression, and of course it is the ions over the unionized form, and I'm plugging in the x's. It will be x squared over 2.0 minus 6. Okay, and now about that approximation method. This is kind of new. KAs are usually pretty small, and so since they're very small numbers, and this one is not as small as some are much smaller, but because they're very small, the X will be a tiny number. The amount that ionizes will be very small. And so this term right here, the equilibrium concentration of the unionized part, will be almost equal to the original. In other words, it'll be almost 2.0. Okay. This X is a small number, and it does matter up here, but the approximation would be to take this and to just put in a 2 there. So the approximation method is to say that the HF initial is approximately equal to the HF at equilibrium. And you will be able to do this approximation. It basically is only needed when you're going to end up with a quadratic equation. And you're welcome to not make the assumption and do a quadratic equation. But anyway, I wanted to show you this way to make this simplification. And so what we're doing, how we a lot of times will write that, is that we're saying that's 0. So I'm going to rewrite with that approximation. Okay, now we can look at it and kind of see, well, what do we have and what do we need? Well, we knew that if we're trying to get to equilibrium concentrations, and that will also allow us to get to pH. Equilibrium concentrations are X, so we need X. Is there any piece of information we haven't used? Because we don't have X. And we do, we have that Ka, the Ka was given, so. And so if we solve this for x, that will be an equilibrium concentration, and we can get them all from that. So, and since we made that approximation, it's going to be pretty simple to solve for x, because we don't have to use the quadratic equation. We can just take the square root of both sides. X has to be a positive number. It's not possible to have it negative, so I don't have to worry about that. And I'm going to carry a lot of digits on this. For now, we know it only has 2. Okay, so from that, I can plug into these expressions here and get my equilibrium concentrations. In other words, and this is the part where we made the approximation, and it ends up, it was a very good approximation, that if we considered sig figs, this would round up to 2. That the equilibrium concentration of the unionized part is almost equal to the initial that we used. Okay, and then for the hydrogen ion and the fluoride ion, they are both equal to x. So, and for here as an answer, I'm going to go ahead and round that. So I have all of my equilibrium concentrations. And then the other question was to solve for pH. So to get pH, I'm going to just use the equation for pH. pH equals the negative log of the hydrogen ion concentration. And here it's a good idea to go back and use those extra digits. And sig fig wise, we really only had 2 sig figs. Remember that on a pH, only the digits after the decimal count as sig figs. So that's it. And you can ask yourself, should I have a pH of 1.43? Well, I don't know, but I know for sure it should be under 7 because it is an acid.